So today our lesson is Stoichiometry 1. I should make you guys say that word all together. It's fun. Stoichiometry. And first of all, what is it? What is this word? What does it mean? We know, like, metry, we're going to be measuring something. We're going to be looking at it. Stoichiometry. Let's just get into a definition that will work for us. It is using balanced chemical equations. So let's write that. Using balanced chemical equations to determine, so using balanced chemical equations to determine the masses of reactants or products. So, using balanced chemical equations to determine the masses of reactants and products. This is a quantitative relationship. What does quantitative mean? Uses numbers, right? So we got numbers. Okay. In this quantitative relationship, uses ratios. So we think about a ratio, we kind of think about we have so much of one thing and then we would need so much of another. How much do they compare? So we're going to compare numbers from chemical reactions, from chemical equations. Alright, what numbers are we going to use? The numbers that we're going to need are the coefficients. Okay? Remember, those coefficients are what you had to change when you were balancing a chemical reaction. And so the coefficients tell us how many molecules we might need in a reaction that we might look at very carefully, but we're never going to look at specific molecules. What we actually are looking at is the number of moles. And we talked about moles with Avogadro's number several times. And we talked about molar mass, which we're going to pull in to use with stoichiometry. So coefficient and number of moles, that's going to give us, and if we really think about it, it's kind of a Mr. Obvious moment, but that's going to give us our molar ratio. Alright. So let's look at a completely generic and made up equation, and we'll kind of talk about it. So if we have 2 of some compound, and it's a gas, and we have 3 moles of another compound that's a solid, they're going to make completely something other compound that's a gas, and something other that might be aqueous. Okay, so I guess in using these generic variables, we're saying it doesn't really matter what the compounds are, because at this point we're looking at the coefficients. The coefficients are the key to getting stoichiometry correct. So if we are looking, remember we needed mole ratio. So what is the mole ratio of A to B? Well, let's talk about mole ratio. If I am comparing how many moles of A that I need for this equation to how many moles of B that I need for this equation, then I know that I need 2 moles of A and 3 moles of B. If I have 2 moles of A and 3 moles of B, how many moles of C am I going to come up with? What's that coefficient say? If there's nothing there, we know that it is an invisible 1, right? And so if I have 2 moles of A and 3 moles of B, how many moles of D am I going to come up with? 4. Right. So this ratio, every time you have this amount of reactant, you're going to have this amount of product. Now, in the real world, we know it's not always perfect. We're not always going to have an exact amount of each of these products, an exact mole, 2 moles, an exact 3 moles. And so that's where the ratio is going to turn into a conversion factor. So we could write it like this: 2 moles of A to 3 moles of B. Thinking about, we've drawn in that idea of conversion factors, how else could we write this conversion? Don't cringe. Here it comes. 2 moles of A over 3 moles of B. Or 3 moles of B over 2 moles of A. Alright. Tell me what you think. Do you think it has to always be the reactants that we can use these ratios with? No. We could have 3 moles of B to 1 mole of C. We could have, and a question might ask you, if you come up with, let's say, 1 mole of C, how many moles of D should you have? So you'd have a 1:4 ratio there. Alright, so this whole concept of mole ratio is really what stoichiometry is about. So we're going to have to be balancing the chemical equations, we're going to have to predict products, and then we're going to have to mathematically compare them. Alright, so that's the first kind of concept that we're going to look at in this idea. Now, like we said, life isn't always perfect. We don't always get 2 moles and 3 moles makes 1 mole and 4 moles. What if I double, just like a cooking recipe? What if I have 4 moles of A and 6 moles of B? How many moles of C will I come up with? Somebody whispered 2. How many moles of D would I come up with? 8, exactly. So if we have this ratio, 4 to 6, of reactants, then we're going to come up predictably with this ratio of products. Okay? We could also go the other way. What if we half it? Like, what if I don't have 2 moles? Okay, what if I only have 1 mole of A? How many moles of B would I need? 1.5. Right. Okay, so just like cooking, when you make a recipe, you can half it, you can double it, you can 57th it. It doesn't matter, but it's a ratio. There's a certain amount per each other amount. So let's finish this line. If I half my recipe, if I half my reactants, how much of my C, how many moles of C will I come up with? 0.5, right. How many moles of D will I come up with if I've halved it? 2, because 4 divided half of 4 is 2. So that ratio will stay the same, just like a recipe. Okay, so let's do an example, and then we'll write down the steps that we see in our example, and then we'll do some more examples, okay? Because in your CK12 stuff, you're going to have to do a whole bunch of these, and again, these dudes kind of take some time. Okay. Alright, so I'm going to go ahead and write the whole question like you might see it on a worksheet, or you might see it. So calculate the mass of hydrochloric acid. And a lot of times for something like this, they will give you the formula, which is very convenient. Hydrochloric acid needed to react with 10.0 grams zinc metal. Okay, so let's go through the model, and you guys listen for the steps, and we'll write the steps down after we do the model. Okay, so the first thing I need to look at is I need to have a balanced chemical reaction. So I need to say, what is going on in this? Calculate. Okay, so hydrochloric acid is going to react with zinc. So I need this hydrochloric acid reacts with zinc metal. Alright, so what is that? They conveniently tell me that hydrochloric acid is HCl plus zinc metal. I know metals I can just write because they are like the electron C model. They don't need a subscript. And then I gotta have some kind of products. Well, in my brain I think about, okay, this is a single replacement reaction because there's one element in a compound. So I know that zinc makes a positive ion. I'm gonna check on my cheat sheet and look. Zinc is a +2. Well, conveniently there's only one option. So zinc is a +2 ion. So when we come over here to we know that zinc is gonna take the place of hydrogen. It's gonna be a +2. Chlorine, we've used enough times, I think we've memorized, is a -1. So when we crisscross those, the charges become the subscripts. I don't need to write the 1 for zinc, but I do need to write the 2 for chlorine. And then I'm going to have my hydrogen is all by itself because zinc replaced it. Now, can I write just the H all by itself and leave it there? I see heads shaking. No. Hydrogen is diatomic. So we have to make sure that we think about that. And now we have to balance it. So if we don't balance the equation, then we should be thinking, well, where on earth did that other H come from? Where'd that other C come from? So we have to balance it. So looking, there's 2 H's, there's 2 Cl's. Conveniently, the compound is together over here, so I can put a 2. Now I have 2 H's, 2 Cl's, and my equation is balanced. Alright, I'm not done. I'm given 10 grams of metal. Alright, so if I have 10 grams of the zinc metal, this is where I start. And it's asking me to calculate the mass of hydrochloric acid. So this is my X in grams because mass is measured in grams. So this is where I'm starting, and this is where I'm going. Well, I can only start with what I have. So I'm going to have to start with 10.0 grams of zinc. Well, we talked earlier about the coefficients are the moles. So, I can't use grams in my example because I don't have any information about the ratio of grams to grams in this. So I'm going to have to change my grams of zinc to moles of zinc. So how do I do that? You got to go back to your periodic table and find the atomic mass of zinc. So we go, okay, zinc 65.39 for 1 mole of zinc. Alright, I've got a good start here. My grams cancels. My grams of zinc cancels. My grams of zinc cancels. I'm left with moles of zinc. That's not what I wanted. So I need to continue. I need to cancel out moles of zinc. And I'm going to come to this molar ratio business. I'm going to have to use the moles of zinc, so the coefficient of zinc, and the moles of hydrochloric acid, the coefficient there. So if I want to cancel moles of zinc, there isn't anything there. So I know that's a 1. And I'm going to come up with, this is my bridge, moles of HCl. So what is the coefficient there? Well, that's a 2. Alright. Is that, oh wait, I didn't want moles though. I want grams, so I'm not even done yet. So my moles of zinc cancel. My moles of zinc cancel. I have moles of HCl. Well, I need to cancel them, so I have to put those on the bottom. And I need to come up with grams, because it asks for mass. Alright, well, where do I find that, right? We have to go back to the periodic table, and we're going to find the molar mass of this. So we could come down here and say, okay, H and Cl, H is 1.0. Now, where on earth am I getting that? Right here. Chlorine is 35.5. I only have 1 of each, so you could probably make that really shorter and just add them together. But 1.0 plus 35.5, that's super easy. 36.5. I just wanted to give you the full example. Okay, now we have one factor label method problem there. So moles of HCl cancel, moles of HCl cancel. I have grams of HCl, which is what I wanted. Now all I have to do is calculate the thing. Okay. So I am going to multiply straight across. Okay. And so pull out your calculator, multiply with me. Okay. And so 10 times 1 times 2 times 36.5 is 730. Now hold on, don't stop there. Now we have to multiply straight across the bottom. And so luckily it's 65.39 times 1 times 1. And we don't have any units because all the ones on the bottom canceled. So then we divide 730 divided by 65.39. We get this number. 11.16378651117 grams HCl. That's too much to write. Not only that, but it doesn't go with the significant figures rules. So, we're given in our problem 3 significant digits. So we want 3 significant digits in our answer. So right here, the 6 tells the 1 to go up. So I have 11.2 grams HCl. Shoo-wee. Okay, that is our answer. Okay. That is our answer. Now, I told you guys to think about the steps that we did. Okay. So I have run out of paper, but we are going to, we'll put the steps right here. Alright. So, these problems take a lot of thinking. What was the first step? Balanced chemical equation, absolutely. If you don't have that, then you don't have the mole ratios and you can't go any further. What's the second step? We'll come over here. We had to go back to our problem, find what we were given, and mark it on the equation. So we could call that label the equation with what you're given. Luckily there's really 3, it just takes forever. The third one, what was all this business? All factor label, right? Like, this is skills that you already know, but it's just putting it all together. Alright, give me a thumbs up if you feel like, yep, you can do this. A thumbs down if you're like, oh my goodness. Somewhere in the middle is a lot of people. Alright. Alright. Let's go ahead and do a couple more examples. And let's see, what time do we leave this class?